So the last in this sequence, and then there's one more gas law to follow, is called the combined gas law, and it's called that because it combines the three laws that we've done so far, Charles's law, Gay-Lussac's law, and Boyles' law, and shows all three pressure, volume, and temperature variables in one equation. So the setup is pretty much the same as it was if you look at the other three. If you have pressure times volume equals pressure times volume, that's Boyles' law. Volume over temperature and volume over temperature, that's Charles's law. And then pressure over temperature is Gay-Lussac's law. So we've got all three of those formulas mixed in with this one. Same rules apply. You're getting values, plug them in, make sure your temperature's in Kelvin, and solve for the one missing thing. There's just more numbers to work with now. And it is worth noting, right, that, like we just showed you, you have all three laws combined in one. So you really could use this one combined gas law to solve any of the problems we've done so far. It would just be that in any one of those, you would either take out the temperature because it's constant, or take out the pressure because that's constant. And then if you take out one variable, you get the other laws. So here this is showing you the same thing, right? Pressure times volume, that's Boyles' law. Well, here that is in the combined gas law. Volume over temperature, well, here's that one. Pressure over temperature, here's that one. So they're all three in the same formula when we do the combined gas law. So here's a gas law, combined gas law problem. Now we've got a lot of numbers to look at, and we need to use them all. So we have a pressure, kPa is pressure, that's our starting pressure. Temperature, which is 30 plus 273 would be 303 Kelvin. And the initial volume, so that's V1. V1 is 2 liters. Then it says the temperature changes, so this is our temperature 2. And the pressure also changes. So now we're manipulating more than one variable at a time. So this is P2. Okay, don't forget to change your temperature here. 80 plus 273 equals 353 Kelvin. So that's the number I'm going to use for temperature 2. This is the number I'm going to use, 303, for temperature 1. So I plug all that in. Let's see if we can squeeze this in here. So 110 kPa, I'm leaving out the units to save space here, times volume 1, which was 2.00 liters, over our starting temperature, which was 303, equals the second pressure, P2 is 440, times V2. That's what we're missing. What is the final volume is the question. All that over 353 degrees Kelvin, or 353 Kelvin. So I've plugged in 5 out of the 6 numbers. And from here we're going to solve to find the missing piece, which is the volume. And what you end up with is volume 2 equals 2 times 110 over 440 times 353 over 303. And you get a final answer of 0.58 liters. And the volume went down even though the temperature went up, because the pressure went up much more than the temperature did. Now normally when the temperature goes up, the volume goes up, and when the pressure goes up, the volume goes down. So you've got these competing forces. But the fact is the pressure quadrupled. It went up 4 times, whereas the temperature only went up by, say, about a fifth, 20% or so. So the fact that the pressure went up way more than the temperature is why the volume went down instead of up. So that is the end of the gas laws, with one exception. We have the ideal gas law to cover next. It's a little bit different from the rest that we've done so far, so we'll talk about that in the next video.